Good morning. So let's go back to looking at membranes. We finished the lecture on Monday with a video from the Sydney Water Treatment Works. And what we're looking at now is just how membranes, and these typically are spiral wound membranes, and how they are organized into a membrane system. And what you see here, and let's just look at the end perspective. And what you see are, again, light granular filtration membranes. Notice that the plumbing is such that you have, for each membrane unit, you've got these two membranes plumbed like this. Again, it's just cheaper to plumb these membranes. The piping is expensive. So if we can minimize piping, we want to do so. So what you see is basically there's 4 banks of membranes. We have 6 membrane vessels. So each one of these units here, or you can see it here, is known as a pressure vessel. And in the pressure vessel are your membrane elements. So the way this is set up is this is referred to as a 4x2 stage arrangement. So we have 4 banks, 1, 2, 3, 4 banks of membranes. We have 6 membranes, pressure vessels per bank. So we have 24 vessels. That's where the 24 vessels comes in. So that's for stage 1. In each pressure vessel are 6 elements. So that's 24 times 6 equals 144. So there's 144 membrane elements in stage 1. And then stage 2 has 12 vessels. So we have 2 banks, each with 6 pressure vessels. Again, we have 12 vessels. We have 6 elements per vessel, and that gives us the 72 elements. We can also describe it with the schematic that's shown here. So what we have these, think of these as the 4 banks. We produce, so this is our product water here. So we're combining all of this product water or a permeate, and we have permeate from the second stage here. And then we have a reject stream. So here is the reject stream. And that reject stream is then passed through stage 2. We still produce a reject stream or a concentrate that has to be disposed of. The last one here is a 4x2x1. So the only difference now is we would take the concentrate or the reject stream here, and we would put that through another vessel. We would again produce reject stream, and then we have permeate that we could then add. What we're kind of think of it this way, that what we're trying to do is squeeze out as much product water as we possibly can, so that we're producing the greatest percentage of that product water. We're minimizing the flow of our reject stream. Now, this means that the reject stream becomes more and more concentrated, which also becomes a challenge. I'm going to play this as a short video I added this morning just to try and give you a little bit greater sense of how water is flowing through these membranes.
Feed enters at one circular end of the spiral membrane and travels down the membrane here, illustrated by the red arrows. Permeate, illustrated by the yellow arrows, and retentate, illustrated by the dark red arrows, leave at the other end of the spiral membrane. As the feed travels down the spiral, it becomes more concentrated, illustrated by the increasingly deep red color of the arrows. This concentration effect is due to the fact that the transmembrane pressure, that is, the difference in pressure between the feed and the permeate side, induces a flow of permeate through the membrane layer. The membrane is constructed such that the permeate is transferred to a perforated central tube known as the permeate tube from which it leaves. It may be easier to understand how this separation takes place by unrolling the spiral membrane, allowing a further look at the membrane construction. The feed can only enter where indicated since the membrane sheets are glued to form membrane envelopes that contain a spacer which ensures that the permeate is transported to the central tube. The spiral module is constructed by attaching a number of properly glued membrane envelopes to the central tube with a spacer in between to allow room for the feed flow, and then by rolling the envelopes such that the spiral is formed. At the outlet end of each spiral, an anti-telescope device is placed to prevent the pressure of the liquid from deforming the membrane shape.
And so hopefully that gave you some sense of how water is flowing through these membranes. So each element itself is producing about between 5 to 15% of the product water. Together, those 6 membranes are what can produce somewhere between about 60% product water. And that's what we're talking about, recovery. Now, if we can get higher percent recovery per membrane, 6 is pretty much the maximum we can have, then we can increase that recovery. So let's look at an example problem here where we have a reverse osmosis membrane and we're demineralizing cubic meters per day of brackish water. That's our flow. Our water permeability through the membrane is roughly 0.21 liters per day per meter squared of membrane per kilopascal. And that's at 25 degrees C. The transmembrane pressure, so that is the pressure across the membrane, is 2,400 kilopascals. The difference between the osmotic pressure in the feed and the osmotic pressure in the product water is 310 kilopascals. You're told that the lowest operating temperature is 10 degrees C, and that the area that you need at 10 degrees is 58% greater than what you need at 25 degrees. Remember, we talked about diffusivity. So diffusivity decreases as temperature decreases, which means we need more area. And what you're asked to do is to determine the membrane area required, and then the number of elements required, or pressure vessels required, if each element has 30 square meters of membrane surface. So let's look at this problem and just write down the parameters. So the Q we have is 760 cubic meters per day. Our water permeability is 0.2068 liters per day per meter squared per kilopascal. And that was at 25 degrees C. So that's provided by the manufacturer. Our transmembrane pressure is 2,400 kilopascals. The change in osmotic pressure was stated to be 310 kilopascals, and the lowest water operating temperature was 10 degrees. And we said that we were told by the manufacturer that the area required at 10 degrees, 58% greater than that at 25 degrees. The equation that we had provided for flux was that the flux of water is equal to Kw times the difference in the transmembrane pressure and the osmotic pressure across between the feed and the product water. So this is simply equal to 0.2068 liters per day per meter squared per kilopascal times 2400 minus 310 kilopascals. And that is equal to 432 liters per day per meter squared of membrane. Area that we need is equal to our flow divided by our flux. So the area that we need is our flow rate divided by the flux. So liters cancel, meters cubed cancel, day cancels, and we're left with units of meters squared. But remember, we were told that it would be 58% greater than what is required at 25 degrees. And this here is at 25 degrees. So that means we need roughly almost 2,800 square meters of membrane surface. And if each membrane has 30 square meters, so this is per membrane element, that means we need 93 elements, which is a significant number of membrane elements. So we can think about setting this up if we have 6 membrane elements per vessel. So this is per pressure vessel. We need 16 vessels. So we can think of setting this up as having 4 banks of 4 membrane vessels each. So each one of these represents a pressure vessel. Each vessel has 6 elements. So we'd have a total of 96 elements in 16 pressure vessels. Any questions about that? When we talk about membrane configurations, we can talk about what is referred to as dead end and cross flow. And few of you were on the seminar that Dr. Tarabara had organized on Monday, and you saw that there talked about cross flow and there's slight modification on how they were accomplishing the cross flow. But with cross flow, with dead end, this is a typical filtration that you would do, actually, coffee filter. Water flows in one direction. And with a coffee filter, you're using gravity as for your pressure. You've got hydrostatic pressure. And the water flow and our pressure are in the exact same direction. And if you've done any sort of filtration, your particles collect on the filter, and your filtrate or your permeate flows through that filter. So that's a dead end. Cross flow, here's our membrane surface right here. Pressure is perpendicular to the surface. The feed is parallel to the surface. We still have particles material collecting on that surface, and the permeate is perpendicular to the feed. And here's our concentrate. So our feed and our concentrate are parallel to one another. Our permeate is perpendicular to that. It's just another image of a spiral wound membrane, just to give you a size of these. So typically the diameter of these membranes ranges from about 0.1 to 0.46, so half a meter in diameter, up to almost a half a meter in diameter. Most common is about 0.2 meters, which is about 8 inches in diameter. So this spiral wound membrane is about 8 inches, roughly 8 inches in diameter. And the length of each element, so the length of each element is typically from about 1 to 1.5 meters, roughly 3 to 4 feet long. And then, as I mentioned, the permeate recovery per element typically is about 5 to 15% per element, which is why we need so many elements in order to achieve the recovery that we're desired. Now, the other thing to recognize is when we operate these as constant pressure or constant flow. We can't have both. Okay? If we have constant pressure, then over time, as that material deposits on the filter, your flow is going to decrease. If we operate at constant flow, then over time, the pressure that you need in order to push the flow through the membrane surface will increase. Operated at constant pressure over time, Q will decrease with time. If we operate at constant flow, then pressure, so that pressure, the transmembrane pressure that we need in order to maintain that same flux will increase with time. And we'll talk more about this fouling layer that deposits on the membrane surface. These are tubular membranes. So here, this is a tubular membrane. So this is shown here as an outside-in configuration. The water flows from the outside. My filtration layer will deposit on the outside. Water flows through, and this is my clean water. In a membrane bioreactor, which is what you see here, this is from a membrane bioreactor. These are the tubular membranes. They're fiber membranes. They're typically up to about 2 millimeters in diameter. So they're extremely small. And then the water is flowing from the reactor through the outside and then is being collected. Now we can also operate as an inside out, in which case these are ceramic membranes and the water flows. So this is our water to be treated. This would be operated in a cross flow mode. So this is the flow, this is our feed water. The permeate treated water flows through the membrane surface and out into a collection vessel, and the reject stream would flow out the other side. So this is our reject. The nice thing about ceramic membranes is they're extremely durable. You can dry these. You can take these out to a far remote location and turn on the system and operate it. Polymeric membranes need to be maintained wet. They're a little more difficult to just take out to such a remote location. Just compare the flow when we're looking at outside versus in. We have a ultrafiltration membrane, and this is essentially what you see. So think of that as a type of membrane that you would see in a membrane bioreactor. You have 5,760 fibers. That is not unusual. Each of the fibers are 1.87 meters long, and they have an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. And your volumetric flux is independent of whether you use a inside or outside mode. And I'm just going to stop and just notice the question. The question is, so when I go backpacking, I take these hand pumps for getting water from streams that have a ceramic cylinder inside. This is the same thing. It is this type of a membrane. So if you have a backpacking membrane and it is a ceramic membrane, this is essentially what you have. One of the things you want to think, they do clog. So you want to clean these after because they clog. You also want to think about if you have a highly turbid water, you don't want to treat that directly. So for instance, back in 2014, when I went it was close to 100-mile backpacking trip down at Philmont with my son through Scouts, I was in charge of water treatment, and nobody got sick, which was really cool. But there was one location downstream from the donkey paddock that there we actually treated the water through. I'm going to ask all of you. Okay, there is a stream. The stream is downstream from the donkey paddock. It is extremely turbid. How should I treat that water? And then I'll tell you what we did. Anybody want to venture to guess? And we did have ceramic filters. We could have boiled it. It would have taken a lot of time, though, and a lot of energy. And we had not a lot of time to get to the next campsite. We could have let some of it settle. That would have taken some time, too. We actually did some of it when we had time at night. We actually pre-filtered it through fabric filters. So we just made filters out of handkerchief type material that we had brought specifically for that purpose. So we pre-filtered it through the fabric filter, then filtered it through the ceramic filters, then added the chlorine tablets. When we were in the higher country and we were treating spring water, typically we then just filtered it through the ceramic filters. It was sufficient because it was both spring water and it was the high country, so there was less potential for contamination. But downstream of the donkey paddock, we needed to make sure that we didn't clog the filters because of the turbidity, removed as much of the bacteria and viruses that we could on the ceramic filters, and then also treated with chlorination to ensure that we killed everything else. And we made sure that when we chlorinated, we let that water stand for the requisite 3 hours to try and make sure that we got the CT needed to disinfect. And like I said, nobody got sick. So that was a good thing. So back to this problem here. So what I want to do is calculate the water production from one module And we'll look at what that production would be if we were to do an outside in versus an inside out membrane. We had 5,760 fibers. The length is 1.87 meters. Outside diameter is 1.3 millimeters. Inside diameter is 0.7 millimeters. So the area per filter, per fiber, is pi d times the length. So that's pi times 1.3 millimeters times 10 to the minus 3 meters per millimeter times 1.87 meters. And that is 7.64 times 10 to the minus 3 meters squared per fiber. So our flux is equal to the specific flux times the area, and that is equal to 75 liters per meter squared per hour times the area times the number of fibers, and that is equal to 3,300 liters per hour. So that was the outside in. The inside out, same equations. The area per fiber, in this case, is pi times 0.7 millimeters times 10 to the minus 3 meters per millimeter times 1.87 meters. And that is equal to 4.11 times 10 to the minus 3 meters squared per fiber. And then again, if we calculate our flow rate, and that's equal to the specific flux, again, times the area. So that is equal to 75 liters per meter squared per hour times the 4.11 times 10 to the minus 3 meters squared per fiber times the number of fibers, and that is equal to 1,780 liters per hour. So if we compare flow outside in to the flow inside out, that is equal to 3,300 divided by 1,800, multiply that by 100, and that is 186%. So the flow that we can achieve with this outside in membrane is almost twice what we can achieve with an inside out. So it's one of the reasons why it makes sense for these membrane bioreactors to use a inside out membrane. Just some applications of membrane filtration. You can take raw water and directly filter it through a membrane filter. This is done in Marquette. So Marquette has a membrane filtration system. I believe it was one of the first surface water membrane filtration systems Monroe was Marquette, I believe, was the first. Mackinac Island also has membrane filtration now. One of the nice things about membrane filtration, especially pertinent to Marquette, is there's roughly 15,000 people on the island per day during the summer. And those people are on the island, they're eating, they're drinking, water's being consumed, so there needs to be sufficient water produced for that population. In the middle of winter, there may be less than 400 people on that island. So you need to have a plant. Think about this with your design. You need a plant that operates as effectively for those 400 people in the middle of winter to that 15,000 that are on the island in the summertime. It's quite the challenge. So both water and wastewater treatment plants have to operate with that kind of variability in flow. You can also use it for softening. In this case, there is in the second one, you have a softening step first, and then a membrane filter for further softening. This here is a direct filtration system. You're applying some coagulant, you've got some flocculation. Notice there isn't sedimentation. So this is again used for pristine water supplies. If you have a large amount of sediment that's produced, that's going to clog the filter very quickly. In this case, this is essentially a conventional treatment plant here, followed by membrane filtration for further treatment. You can also combine it with reverse osmosis. So for instance, you can have a microfiltration system or an ultrafiltration system followed by reverse osmosis for targeted removal of certain pollutants. So as I mentioned before, in terms of the operation, you're going to get a layer of particles depositing on that membrane filter. We refer to that as the fouling layer. We also talk about it. Filtration cake gets a little more complicated. I'm not going to go into the difference between, but basically know you have material that's depositing, and that is going to inhibit flow. And that's why if we operate at constant pressure, the flow decreases over time, or if we operate at constant flow, we need to increase the pressure over time. We can also have scaling. This is different than fouling. This really is the result of exceeding the solubility layer. So here is our membrane surface. So water's flowing through that membrane surface. We have concentrate on this side. So the water's becoming more concentrated. And then what we have here is we can have a concentration gradient develop on that membrane surface. That results in higher concentrations of more insoluble materials, and then they deposit on the surface. So you get these precipitates, and that results in scaling. So it's scaling like we've talked about before, but in this case, it's scaling on the membrane surface. That can be very, very difficult to remove. It often requires extensive cleaning to remove that scaling layer. You can also have precipitation. So for instance, if you have reduced iron and that iron is being oxidized, then what you can end up with is a membrane that looks like this. So what's happened is that iron has oxidized from Fe2 plus to Fe3 plus, precipitated out as FeOH3. And you can probably imagine getting flow through that membrane is extremely difficult. When about 20 years ago, membrane filters were put in Chelsea. They didn't put in an iron treatment system. And within a few weeks, the membranes all looked like this. They then had to go back in, retrofit the plant in order to remove iron prior to filtration in order to prevent this. The other problem that we have is what's referred to as biofouling. And here what happens is you get microorganisms that attach to the membrane surface. Those microorganisms colonize the surface. They grow. They can release what we refer to as extracellular polymeric substances that coats the membrane surface. And as you can imagine, getting flow through that membrane becomes increasingly difficult. So because of all of this, in many cases, we pre-treat the water prior to feeding it on to the membrane or into the membrane. So we can add antiscalants. So these are chemicals that are used to inhibit precipitation or crystal growth, to keep the chemicals that would precipitate in solution. So they could also sequestration agents, again, to keep these chemicals in solution. We can pre-filter. So we saw that with, for instance, with the RO, where there was a membrane filter, perhaps a microfiltration process before the reverse osmosis system, so that you're filtering out those particles prior to the RO unit. So you're minimizing fouling on the membrane unit. You can also add sulfuric acid to adjust the pH or caustic soda to adjust the pH. And here what you're looking at doing is changing the solubility. So you're trying to make whatever is precipitating, you want to prevent that precipitation. The other thing is, which isn't here, is disinfection. And as Austin just mentioned, here what you're looking at doing is you're trying to kill the microorganisms to prevent excessive biofilm accumulation on the filter itself. So you're trying to prevent that biofilm growth. It's one of the reasons in the engineering building, if you go to the lab, there's the DI water and there's the regular tap water. You don't drink the DI water. And it's because of the chemical disinfectants. They used to use formaldehyde. I'm not sure if they're still using it, but they disinfect in order to prevent biofilm growth on the membrane itself. And then finally, I mentioned cleaning. Fouling will occur. It's almost inevitable. And so once the fouling occurs, then you need to clean the membrane, and that is typically done with acids or bases, or in some cases, a combination of both. And then you also may, again, disinfect to prevent biological fouling. And finally, the water that you're producing, especially if you're using reverse osmosis or nanofiltration, is essentially devoid of minerals. So I showed you the images from the pipes in some of the residence halls. Once that water is passed through the RO, there's essentially no minerals in it. It will typically have a low pH, as the alkalinity is also removed. The water is highly corrosive. So typically what you need to do is add a base. You want to add alkalinity in many cases and a corrosion inhibitor. Also, if you can, you have an RO unit, for instance, a below the sink RO unit at home, you want to use plastic piping. And if we could be in the engineering building and we could actually go look at the RO system, you would see that the RO water is all transported through the building with plastic piping because of the challenges related to the corrosivity of that water. The other challenge is, what do we do with this concentrate? It has a high total dissolved solids. We potentially can discharge it to a municipal sewer, but we need to be very careful with that, because if we change the salinity of our water, that has an impact on microbial growth if we're using activated sludge or trickling filters or etc. Oxidation ditches, it's going to affect the microorganisms. We can look at ocean discharge, but again, we have to be very, very careful, because if we discharge too close to the surface, we can actually change the salinity of the water in the estuary, which then impacts negatively the aquatic ecosystem. And in some cases, new RO systems have actually been banned because, or a moratorium placed on new facilities because of this impact on estuary ecosystems. And then lastly, we can look at deep well injection. So hopefully that gives you some sense of membrane systems. We'll start residual management on Friday, and I'm happy to stay online if anyone has any questions.